So I'm going to start the recording here. I've given you some problems to address last time as part of this for the take-home exercise. So in one case, we said the starts empty, and then we have some rates of flow in and out. One rate was 2 flowing in and 1 flowing out. So what is the stock going to do over time? It's going to increase, and how will it increase? Okay, 1 every month, good. So it's going to be rising. The value of the stock, it's going to start at 0 and it's going to rise linearly every month, right? It's not quite a perfect line. I'm an imperfect artist in graphs. Okay? But it's going to rise. So this is going to be month, and this is going to be the dollars, right? And it's going to be something like this. So by month, and it's going to be at $n, right? Something along those lines. Good. Okay. How if we had something like, and why is that? Well, the net inflow is what here? If you take the flow in minus the flow out, it's what? It's 1. And hence, the rate of change of the stock is 1. Now, for those of you who are really comfortable with remembering back to your calculus, which is admirable and will be very handy, what we're talking about is the derivative of the stock is 1. If you call the stock x dx dt, the rate of change of the stock per unit time is equal to 1, equal to inflows minus the outflows. So in general, we could write down dx dt equals the sum of the inflows minus the sum of the outflows, right? And this is going to be really handy for us at quite a few points in the semester. Okay? This is the rate of change, how fast it's going up in terms of dollars per month. It's rise, or if it's negative, it's drop. So if it's minus 10, we're losing $10 a month. If it's plus 100, we're gaining $100 a month. Make sense? Okay. How about this next one? What is the stock going to do in this case?
Initially, the stock will decrease because the net outflows are greater than the net inflows.
Good. Okay, so suppose I were to, let's be fair to the sides of the room. I'd like to do some things you folks can see a bit more. Okay, so the stock here is not starting at value 0. I think it's value 100. Okay? It's starting at value 100. And 0 is down here. And what's going to happen over time? Initially, it will be dropping or going up? Okay, so this is the inflow is in blue, and the outflow is in red. So which is bigger? Is inflow less than the outflow or greater than? Less than. Therefore, the stock will be dropping, right? The outflow is greater than the inflow. The stuff is going out faster than it's coming in. It's going to drop. It's a giant sucking sound that Ross Perot talked about. Cheryl can remember that. I'm not sure anyone else can. Okay, giant sucking sound south of the border. They were talking about a different border though. Okay, so ladies and gentlemen, it's going to be dropping, and is it just going to continue dropping at 10 per?
No, the rate goes down.
Okay, it'll be going down in what way?
The rate of decrease will lessen, so it'll slow down.
Okay, so it'll be dropping, and it'll be going dropping slower and slower. The slope of this line, which is that derivative, right? Slope. This is the slope, right? It's the slope of a graph, by that I mean a sort of figure over time of x, okay, of x over time, of x as a function of t. The slope of it will be initially at 45 degrees, and excuse me, not at 45. It'll be at minus 10, and then it will get sort of go down slower, and then will it level off? Where will it level off?
At 10 months.
Month 10, it's going to level off. Okay. So at that point, the inflow equals the outflow, and it won't be going up, it won't be going down, because the water is coming in as fast as it's going out. And then what's going to happen after that?
It's gonna rise slowly at first and then.
Okay, it's going to rise slowly at first and then faster. Okay, good. So by month 20, how fast is it rising?
10 units per month.
Yeah, so we could kind of draw a tangent line here, and this is going to be a slope of 10 per month. Okay, that may be dollars or something, right? $10 per month, what have you, depending on the unit of the stock. Okay, good. So stock and flow here, problem. Okay, now I'd like to pose to you another question that relates to this. And this question is actually a classic one which has been given to many classes. Okay, so ladies and gentlemen, this graph shows the number of people entering and leaving a department store over time. Okay, so these are the number of people per minute entering that store in a given minute. And these, in the red, is the number of people leaving the store. You can see the labels up there. Black is entering, and red is leaving. Okay. So I'd like you to answer the following questions. During what minute did the most people enter the store? I'm not talking about net people. What minute did the most people come in? If you had a people counter at a sort of at a doorway, when would the most have entered?
4.
Okay, time 4. Why do we know that? Well, the value of entering is the highest, right? Good, good. During which minute did most people leave the store? We had that counting people going out. If there was an out and an in, and we were only monitoring out. When would the most people leave the store? When would the most people leave the store?
1.
What? Minute 1?
Or wait,
21.
21. Okay, 21. Yes. Yeah, I was getting worried. Okay. Okay. Good. Good. Minute 21 is highest. Okay. When were there the most people in the store?
minute 12 or minute 13.
Okay. So here are a couple different minutes. Minute 8, you might think.
When were the most people in the store?
When were they most in the store?
13 or 12 or something?
Okay. Okay, so let's think this through. So 8, we have a big difference between the entering and leaving. The net inflow is highest. The most people coming in. It was increasing on a per minute basis by the largest amount at that time, because the gap between these was the largest, right? We have the biggest gap between inflow and outflow, so it's going to be rising very quickly there. But in terms of when is it actually reached the maximum value of people in the store, what minute would it be?
Where they cross.
Where they cross here. Because all through this period, what's going on? All through this period up to about minute 13 and a half or so, what's going on?
Their stock is rising.
The stock is rising. We have more people coming in than leaving. So the net flow is positive, means the stock is rising, right? It's going to be rising up here. And it's going to be rising at different slopes for kind of these different time periods. But fundamentally, it's going to be rising all through this first period. And then after this, it's going to be what? Dropping. It's going to be dropping beyond that time period, okay? So we know the most people are in the store here. How about the fewest people in the store?
30.
Okay, so give me two candidates for the least people in the store.
0.
0 and then 30.
Okay, 0 and 30. And in order to distinguish those, what would you have to do to figure out which of those is actually the fewest people?
You'd have to know the initial amount of people in the store.
Okay, it might be useful to know the initial amount of people, but I would argue that that's not actually going to be the determining factor about which one is bigger, because there could be 1 million people initially in the store. Well, okay, that's strange imagination, but even Macy's would have a trouble with that. But you could have a lot of people in the store initially, and the net, you're either going to have more people at the end or fewer people, because what you're dealing here with changes in the number of people. So yeah, how would we figure out if they're more at the beginning or end? What might clue us in?
You'd have to know if the rate of people entering from 0 to 12 is bigger or less than the rate of people leaving from 14 onwards.
Okay, good. The net, yeah. Okay, fair enough. So if we were talking about net rate of people entering here compared to the net rate of people leaving here, which is larger, we could ask if this area kind of between these two curves for the okay, for the later half, this sort of area, mumble. Oh gosh, the system went off. Okay, ladies and gentlemen, it's a systems problem. Okay, and we are encountering challenges. Okay, let me frob the settings. Okay, signs of life. Here we go. Okay, come on. We have to go through and reset it kind of twice in the process. There we go. Okay, so ladies and gentlemen, so we'd like to know, is the area between these two curves here, what? Is it bigger or smaller than this area? If this area between these curves here is bigger than that area, what would that mean?
More people left.
More people left than came in which case, when would there be the fewest people in the store?
At the end.
At the end. On the other hand, if this area were larger than this one, it wouldn't appear that's the case visually, but if this first area were greater than this one, when would there be the fewest people in the store? At the start, because we wouldn't have gotten down, if this area were smaller than the one on the left, then we wouldn't have drained it down even to the level it had at the start, right? Because we're reasoning here about stocks and flows. So you folks may be surprised that this question has been asked at many classes around North America, including many staffed only by graduate level students, including some from very, very technical background. And within this context, people often make mistakes. We have to think through these issues, and it requires thinking through carefully. People's eyes naturally get drawn to extrema, when it's highest, when it's lowest, they get drawn to big gaps or what have you. And you've got to think through the stock and flow reasoning to develop confidence that your answers are on side with the truth. Okay, so all these can be determined, and they can be determined by simple reasoning, but you got to be focused in. And what I hope this is illustrating again is that the maximum for a stock is quite different from the maximum from the rates. You can have a very high rate of flow into a stock, but that doesn't mean the stock is really high. You can have a very low rate of flow into it, but the stock could be very high. There's this relationship between stocks and flows that's often indirect, and that can confuse people. Okay, so ladies and gentlemen, let's call up any logic. Let's get the blood flowing, if we could. Okay, so I'm going to go and call up any logic, and I would invite you to do the same. Okay, so there we go. Here's any logic, and I'd like you to call it up on your computers. So, meanwhile, whilst your computers work, I can get your brains working too. Yes?
Can I ask you a question about the graph?
Sure. The one on the
Yeah.
board or the
curve, the one on the board.
Yes.
What's the curve and not straight line?
sorry, why is it a curve?
Yeah.
It's a great question. So let's go take a look at it. And it's Alexandra?
Yeah.
Is that right? Okay, ladies and gentlemen, why is this a curve and not a straight line? Okay, so sorry, I skipped forward through a bunch of slides. Let me go back to this. So for this, excuse me. Okay, I was combining the slides with illustrations from this exercise. So let me get that exercise up again. Okay, here we go, and there. Okay, so ladies and gentlemen, does this? You were saying this one increases in a fixed way. Why is this one a curve? Why does the value of the stock not changing in a straight line here? So this is the value of the stock. So level of stock. Sometimes stocks, incidentally, are called levels. They also go by the name state variables. They also could be called compartments. Just covered it up. Okay. Ladies and gentlemen, why are we dealing with a curved trajectory for that stock? Here, can anyone provide an intuition for it? The net flow is not constant. That's a good way to put it, because it's the net flow that determines the what of this line? The slope, right? Okay. Another way to put it is that because the net flow is not constant, the stock is going up, sometimes faster, sometimes slower. In order for it to be a straight line, that would be associated with a change in the stock per unit time that's fixed. Okay, so if the slope of this is, let's say, it's clearly negative here, minus a, something like that. Then we have, dx dt equals minus a. The stock is going down by a units for every unit of time. That's going to be delineating a straight line. If, by contrast, we have a situation where sometimes the stock has a big net rate of outflow, sometimes the two are equal, and sometimes the inflow is greater than the outflow, then it follows that the slope will be different at different points. It'll be rising on a per minute basis, or month basis, it'll be rising at different rates at different points of time. Does that help? Yeah. Okay. So it's a good question. Here, by contrast, it's a fixed inflow, and we have it changing by a straight line. Okay, good. Okay, so let's go over to any logic. And ladies and gentlemen, I would like you to go and call up a new model. Okay. So we can close this one out. Boom. And we are going to create, once again, a first order delay. Okay. So this is going to be first order delay model 2. And the time units of this model are going to be days. Okay. And I'd like to use this to rehearse what we've learned, and I'm going to tie this into the little exercise. Okay, so in that exercise, and this is in the final part, I said consider a stock. A stock in a very particular situation. So over here we have a stock P, and there's a flow out of the stock, an outflow, whose value is proportional to stock. Meaning, if the stock is doubled, the outflow does what? It doubles, yeah. It's proportional to, meaning it's just a constant times whatever this is, okay? So here's our flow, and we like to represent that with that. And this depends on some constant alpha, so this is the formula for this outflow is alpha times P. So if this P were measured in persons and our time unit is days, what is this going to be measured in? Days, yeah. So what is alpha times P going to be? People per day, okay? People per day, okay? And the unit of alpha is going to be 1 over day. You can think of it as kind of probability per day that you're going to go on. Okay, that's why it's 1. If we have probabilities, it's like a fraction of coin flips that turn out heads. It's like number of heads over total number of coin flips. It's dimensionless. It doesn't have a it's unit. It doesn't depend on any unit. So it's unit 1. This is a per day rate, probability per day that you're going to transition. And you multiply that times P, which is measured in persons, you're going to have people per day. And that's what you need. Remember, flows are always a rate. It's something per unit time. And that something is the unit associated with the stock. Okay? Okay, ladies and gentlemen. So we have this sort of situation. We saw it last time. So this depends. Remember, we draw these nice dependence arrows. We could see visually what it depends on what it depends without seeing all the gory details unless we want to. But here it's going to be alpha times P. And we're going to have an inflow here. And I can't remember, did I call the inflow B? Like burst, something like that, okay? Okay, so ladies and gentlemen, we have B coming in and alpha times P going up. So as this stock goes up, let's remember from last time, as this stock goes up, what's going to happen? Is it going to?
We'll have more people going out.
Okay, so let's suppose we have a rate of B coming in. Let's suppose 10 people, suppose the stock is initially empty and we have 10 people per day coming in. What's going to happen? Is inflow greater than outflow or vice versa? Well, okay, the flow, the stock has 0 people in it. The rate is 10 coming in per day. 10 per day.
Inflow is bigger than the outflow.
Okay, inflow is greater than the outflow, so what's going to happen to the stock?
It's
It's going
gonna rise.
to rise. The outflow of the stock is alpha times P. P is 0, so alpha times P is 0. So the inflow is greater than the outflow. We have 10 people come in per day, none going out per day, so the stock's going to rise. And what's going to happen over time to that stock? Is it going to just rise linearly? Ad infinitum at 10 per day? No. Why is it going to go slower?
There'll be an outflow.
There'll be an outflow. The outflow is going to be getting, over time, what's going to be going up? The stock value is going to be going up, and therefore the outflow value. And therefore the outflow will be getting closer to the inflow in value. And therefore the stock will be rising, but at a slower and slower rate. The excess of the inflow minus the outflow is going to get smaller and smaller. Whoa. Okay. That was not intentional. It never goes down in this depiction. So what's going to happen over time? If I drew this out, it's going to go up to what? It's going to be approaching some equilibrium value where it doesn't change anymore. That's what I mean by equilibrium. There's multiple terms for an equilibrium. Another term that's sometimes used is a fixed point. It's a situation where the values of the stocks aren't changing, and there's a mathematical notion of fixed point that actually underlies that and other uses of that term fixed point that I'm not going to go into, but I'm happy to discuss in office hours for those of mathematical effect. Okay, so the question I asked, the question I posed, the question, ladies and gentlemen, with which I challenged you, the riddle with which I left you, was what's the equilibrium value of this stock? What is the value that this stock will tend towards which it will tend? Yes?
B divided by alpha.
Okay, good. B divided by alpha. And whence did that come? How do we know that that is the case? Let's reason through. So I'm saying that the equilibrium value, maybe we'll put P star here, a sort of special value, or we could say P of infinity. Mathematicians would probably, they might lynch me, so I'm not going to say that. P as time approaches infinity is equal to this. Okay, so why is it'll approach this? Why is that the case? First of all, how can we verify that that's an equilibrium? Yes?
Well, we can reason through it by saying that when at that equilibrium point, P will equal P and alpha P will equal B because they have to.
Good. So at that equilibrium, if we say what's the rate of this outflow at that point, alpha times P star will equal what? Well, it's alpha times B over alpha, which is equal to B, which means that the outflow equals the inflow. So that's the rate at which the alpha equals, at which the outflow equals the inflow. And in fact, I would posit that that's how you would solve for this, right? You would say, okay, what's the value for P at which these two are equal? So you'd say, well, okay, B, whatever that value of P star is, it's such that that has to be equal to that. The inflow has to equal the outflow, and that allows you to solve for P star as B over alpha. Comfortable with that? Okay. This is the first of many equilibria sort of issues that we're going to be doing. Now, what happens if I perturb this from the equilibrium? What happens if I knock it around? I suddenly were to remove people from it. What would happen? Good. It will work its way back towards equilibrium. So it will bounce back, ladies and gentlemen. Ladies and gentlemen, it will bounce back. Okay. So let's go build this again. We built it last time, but we will build it again to rehearse our skills. Okay, so here's our P. Here's our P. Boom. And we're going to drag in an inflow, ingloriously named inflow, and an outflow called outflow. Okay, and we're going to have a parameter, call it alpha. And we are going to show that outflow depends on that parameter by drawing links between them. Now, I went through that pretty quick. Whence did I go? Whither did I go? I went, ladies and gentlemen, to this element of the palette here, system dynamics, okay? And then I dragged in the stock, and then I dragged in the flows such that they were positioned so that their tips turned green, okay? If you missed it and you got something like that, just drag the tip over there. It'll connect, although it may not make that sound. And then you drag in, then I dragged in a parameter. I called it alpha, and I dragged in two links here that indicate dependencies, okay? And now let's fill this in. Ladies and gentlemen, we're going to fill in an inflow with a rate of 10. We're going to fill in an outflow here with alpha times P. And ladies and gentlemen, we are going to fill in alpha with a default value of 0.1, okay, and 0.05, okay, and we're going to fill in P initially 0. Okay, so what would the equilibrium value of the stock be? So remember, alpha is 0.05, and the inflow right now is 10. So if I run this model, to what value will P be attracted? Towards what value will P find, in what value will it find stability? Will it find sort of a balance where inflow equals outflow? At what value of P?
What is alpha, 0.5 or?
0.05. 200. Good. Because at 200 times 0.05 gives 10, which is the same for the outflow, which is the same value as the inflow, right? It's 10 people per day. Okay, great, ladies and gentlemen. Let's run that. Let's test our intuitions here, right? And then we're going to build on them in a couple of different directions. Ladies and gentlemen, here we go. So here we go. We'll watch that stock. We'll watch it grow. Is it growing linearly? No, it's starting to exhibit curvilinear features, right? Okay. There we go. We see them ever more pronounced. And you notice whither it trends. It's going up towards 200. If I run this, will it ever fully reach 200? No. It'll never fully reach it. It'll successfully approximate it. And you can see it's regrettably poorly kind of truncating the time here. Okay, let's perturb the stock. Let's pause it for a second, perhaps. And let's use this little thing to perturb it. I want to lower the stock to 50. What's going to happen now? And now let's go back to the graphing mode. What's going to happen? It'll drop and bounce back. Do you see this? Okay, ladies and gentlemen, it's coming back to that point of stability where it's in balance. Just like if we were chilled out, our bodies will suddenly heat up. Once I was canoeing in the Churchill River, and our canoe tipped over in a rush of when we were trying to cross a very fast-moving stream that was one of the tributaries to the river, and I fell into the water. And I was submerged I was in the water for about 45 minutes, and this was in June, late June. That water had been, under a coating of ice about a month earlier. So I got out and clothed myself and ate some things, etc. But that evening I had what felt like a really, really high fever, really, really high, a lot of heat. And my body was clearly kind of making up for the extreme chilling by producing a lot more heat. It had geared up its heat production because I was in this very cold water to stay in balance so that I wouldn't encounter hypothermia. And so it is with a lot of systems. They have this kind of balance. This system is one that's in a sort of balance, and if we perturb it, it will recover. Okay, so ladies and gentlemen, suppose we were to drastically increase the stock. What will happen then? We increase it to 500. What will happen then?
It will fall rapidly, is it?
Why will it fall rapidly? Let's go through the reasoning. I want everyone to be rock solid on this before we start looking at more sophisticated systems. Why will it fall very rapidly? Let's go through mechanistically what happens. At 500, what's going to be the case?
Your outflow is going to be greater than your inflow.
It's going to be greater than the inflow. Not only greater, it's going to be much greater, right? What's the rate of outflow going to be? 25 compared to 10 coming in. So what is that going to lead? To the stock to drop suddenly, right? It starts dropping down. But as it drops down, as the stock starts dropping, what's going to be the case? Well, the outflow is going to be doing what? It's going to be decreasing. So as the stock is decreasing, the outflow is going to be decreasing. After all, it just is proportional to the outflow. It depends on a constant times proportional to the stock. Just is a constant times the value of the stock. So the outflow will be dropping too. And so the gap between inflow and outflow, the degree of excess of the inflow over the outflow, will be smaller and smaller, and therefore, if the outflow over the inflow will be smaller and smaller, and therefore the stock will be going down, but by what? Slower and more slowly, right? And that's exactly what we see. So we can knock this thing around. You don't even have to pause it if you are so inclined. And, you will find it recovers its equilibrium. Okay? A feedback system, ladies and gentlemen, a feedback system. A system that is self-stabilizing. And what sort of feedback is this system exhibiting?
Negative.
Negative feedback indeed. Negative, the higher the value of P, the higher the rate of outflow of P, therefore it tends to bring P down. You increase P, it leads to the outflow to increase in a way that means the net increase in P is less than you'd anticipate. It pushes back against that change if you increase P. If you decrease P, the outflow will drop, and therefore P will tend, therefore, to be higher than it otherwise would have been, and therefore it'll tend to sort of dampen the original effect of the change out. Does that make sense? Again, I want people rock solid at this. Okay, now we're going to have some fun. Well, okay, if that wasn't fun enough for you. Okay? Ladies and gentlemen, let us now go to inflow, and I'm going to pose a couple things. So, ladies and gentlemen, instead of making inflow 10, I'm going to make inflow, if time is greater than 20, we'll make it 10.0, otherwise 0.0. So you'll recognize this expression. What does this expression mean? What does this expression mean?
It says that if time is higher than 20.
Yeah.
Then it sets the value to 10. Otherwise, it will be
Yeah. So this expression, like all Java expressions, evaluates to a value. It computes a value. It's a formula, and the value of this formula will be 10 if time is greater than 20. Otherwise, 0. This is called the ternary operator in C and Java, and it's kind of similar to an if-else operator in R or other similar packages. Scala does away with it and just uses an if expression, and it's because all statements are expressions in that language. But okay, so ladies and gentlemen, what if we ran this? I'm working step by step here. What are we going to see? What are we going to see now?
The system will stay at rest for 20 seconds.
Good. And then what will happen?
Go back to normal, or
Okay, all that's going to happen is it's like we began at time 20, right? This is like our previous starting point, time 20. We've just shifted things forward by 20 time units, right? Before it started at 0 at time 20 and the inflow started immediately coming in. Now it's starting at time 20, right? Okay, ladies and gentlemen, let's this drawing of things like that is for the birds. So let's go create a graph here. Let's go to the palette, and let's go to the analysis palette, and let's draw ourselves a proper graph. Let's draw in a time plot, okay? Time plot. And this is going to say it's going to be stock plot, okay? We'll say we'll just say time plot. Okay, time plot. Very good. Okay, ladies and gentlemen. Okay, so we're going to add a data item here. So whence did I go? I went to the analysis palette, which kind of has this thing that looks like a histogram or bar chart here. Went down to the palette and I dragged in a time plot. Okay? So we're going to go add a data item to this time plot, and that is going to be P. It's going to be title of P. How did I get that? I used this plus. And its value is going to be this dot P. Okay, I'm going to start using this. It's the P within me. Okay? Ladies and gentlemen. It's going to update data automatically every 1 time unit, and we're going to display up to 200 days. So it's going to be a time window of 200 days in the scale area. The scale area, make it a time window of 200 days, and display up to 200 latest samples. Here. Ladies and gentlemen, let's run this model. So we've just wired this up to refer to P. It's the stock value of P. Are you people comfortable with that? Speak in one voice.
Yeah.
Okay, thank you. Thank you. Okay, stentorian response. That's great. Okay, ladies and gentlemen, do you need me to pause on this further? Speak in one voice. No.
How have you set the units in your data update section of your plan?
Good question. Good question.
Are they left as seconds, or did you change them to years?
Well, okay, so very important point. If you saw seconds here, it's probably because you didn't set the units when you created the model, and it's very important. I'm just so grateful. Remind me, I can't see you behind there. Rowan. Okay, so Rowan, if you go to the model as a whole, make sure that your model time units are days. That'll be our yardstick for measuring time, but it provides the default time unit for use for lots of things we drag in. So make sure it's days for the model as a whole, and then make sure, Rowan asked a key question, I'm just so grateful for it. Make sure that your model is using days and the update time is in days. You don't want to be using a model that is, in days and the time unit update is in seconds. That would be adverse, okay? Do you see that? Okay, make sure it's in days here for the update times, okay? Okay, so ladies and gentlemen, let's run this model here. Any further questions, further requests? Okay, ladies and gentlemen, let's run this model, and I'm right-clicking on this screen so I can actually go see here. Okay, so we're running this again. The inflow is not gonna come till time 20. Here it is, it's rising, and it's going to rise up, and I am going to stop it. Now let's have this model stop at time 200. So if you click on the simulation, ladies and gentlemen, and you go down to the section called model time, you can set it to stop at a specified time and set it to time no less than 200. Okay, how did I do that? I went to the simulation, that's the experiment or the scenario, and you scroll down in properties to model time, and you set it to be stop at specified time with stop time 200. Do you see that? Okay, ladies and gentlemen, let her rip. Okay, let's try that, and there we go. Okay, now let's continue, ladies and gentlemen, to engage in frobbing behavior. First of all, let's run it out partway through. Okay, so I set this to virtual time mode to run as fast as it can, run flat out. I'm instead of doing that, I'm going to set it to do it at normal time. Instead of doing this, I'm going to just set it to proceed like this. Maybe I'll speed it up by a little bit, have it start going. And you notice I can engage in frobbing behavior. I'll frob the stock here, and I'll change it to be back to 50, and it will drop down and come back. I can change it to be, 300, and it'll come down there. So you can see this goal-seeking behavior associated with balancing feedbacks. This is goal-seeking. Are you comfortable with that? Okay, so ladies and gentlemen, here we see this behavior. Now, I want to highlight something, though. If we drew out, and maybe we'll do it in the same graph here, okay? No, maybe we'll copy that graph. So take that graph, right-click on it and say copy. Right-click and do copy, and then click above it, and then do paste. Boom. And for the top one, I'm going to say time plot flows, and I'm calling it time plot flow. So what did I do? I right-clicked into this and did copy, and then I clicked up here and did paste. By the way, a slicker way to do it yet is to do Control drag, and it will actually duplicate it instead of how you do copy paste, and it will put it just where you drop it. Control drag while you're dragging it, it will actually copy it. I'll just show you so you can see what it looks like, but then I'll delete that one. I'm pressing Control and do it. And probably on Macs you have to use Option or Command, one of those two. But in any case, that's an even faster way to duplicate things, and it's more reliable because you could drop them where you want. Okay, ladies and gentlemen, time plot flows. I want to plot out inflow, and I want to plot out the outflow. Okay, inflow, and I want to plot out the outflow. And I'm doing this to teach a principle of first order delays. In fact, ladies and gentlemen, the motivation no less for their name. Okay, ladies and gentlemen, so what did I do? I copied this graph. I showed you two ways you could copy it. One with control drag or command drag or option drag, whatever it is on Macs, and another with right-clicking copy, clicking somewhere else, doing right-click paste. After that, I called it time plot flows, and instead of plotting P, I plotted inflow and outflow. Okay, ladies and gentlemen, let's run this thing. What should we see now? Okay, good. So ladies and gentlemen, we're going to be running it up to time 20. The inflow is what? 0. And then starting at time 20, the inflow is what? 10. And here's the outflow. Do you see that? Do you see it rising up here? Ladies and gentlemen, let's go now, and we're going to frob this model a little bit more. Here's the inflow. It shot up to 10 and continued on. Okay? Upshot in this case, it's not the Spectre bark, but it's the inflow. And it went along. Here's the outflow, okay? Ladies and gentlemen, let's go now and change the formula here to be, we're going to change different alphas, okay? In fact, we are going to copy the simulation and we will paste it in with a different assumption about alpha. Remember, with scenarios, we can specify different values for the parameters that live in main. So this one is going to be high leaving hazard. Okay, high chance per unit time of leaving. We're going to have a chance per unit time of leaving of 0.5. Okay, instead of 0.05, 0.5. Okay. That compares to this one here, where it's 0.05. We're going to call this simulation baseline. This is going to be our reference simulation. We're going to copy it once more. So we could again do copy, right-click on it, paste, and we're going to create one with a low hazard rate. Okay, so this is going to be called low leaving hazard. So there you're going to have a low chance of leaving per unit time. And it's going to be, it died. Okay, okay, it bit the dust. Okay, let me call up AnyLogic again. The Linux version of AnyLogic is known to exhibit problems where it will bomb out when you're changing the values of scenarios. I don't think that occurs to the Mac or the PC version, but it's an unfortunate truth. Okay, ladies and gentlemen, so you can help me reason while my AnyLogic is still coming up. You can help me reason, what will the impact of changing alpha be? Sorry? Good. The equilibrium point will be lower or higher. I love it. I love it. Congrats. Your name? Yeah. Janelle? Janelle. Great, Janelle, you're bang on. So changing the value of alpha is going to change the equilibrium point. How do we know that from what I wrote up here?
Because alpha's the unique.
Yeah, this is the equilibrium value, right? The lower the value of alpha, we have less chance per unit time of leaving. chance per day versus a 1% chance per day. What is that going to mean? In order for the outflow to equal the inflow, what's going to have to be the case about P? Much higher to get that same match to the inflow, right? Okay, so that's exactly right. So it needs to be higher to have the outflow match the inflow. So as the alpha becomes smaller, we're going to have a higher equilibrium value for the stock. It needs to be higher to have the same outflow. And okay, so sorry, okay. So pardon me while I just go and recover my model. Okay. So this should be. I may just recreate it because it would be really quick to do. Okay. Model. Come on. Models. Oh, it's okay. Okay. Models. Here we go. Boom. And boom. First order delay model 2. Here we go. Boom. Okay. I want to replace it with the automatically saved copy. AnyLogic actually does have auto saving, which is kind of nice. And here we go. And here's our low leaving hazard. Great. Okay. So, ladies and gentlemen, I fear modifying it though, because I think it's going to die again. Okay, so what else? Let's examine the baseline. You folks can tread where I dare not by looking at all three. Okay, so I'm going to look at baseline. The baseline equilibrium value is going to be what? Do you remember? What was the equilibrium value of the stock? Here. Sorry? Up to what value did the stock go? 200. Good. Okay, how about for the high leaving hazard, where we had a leaving hazard of 0.5? What is the equilibrium value of the stock there? What value of the stock is needed for the outflow to equal the inflow? The outflow is alpha times P. The inflow is 10. So what does P need to be to have alpha times P equal 10? 20. 20 indeed. So let's go run this. And it makes sense because the alpha is just 10 times larger, and therefore the equivalent value is 10 times less. Okay, now you'll notice this outflow here. You'll notice the outflow is now quickly mirroring this increase in the inflow. Do you see that? Previously, you notice how it goes up and then quickly reaches. So, ladies and gentlemen, when the stock is at equilibrium, what is the outflow doing? Is it continuing to rise? What is it at? It's also reached a plateau. And what is the plateau that the outflow reaches when the stock is in equilibrium? What's the plateau that the outflow is at as well? The inflow. It just goes up to the level of the inflow. Ladies and gentlemen here, mark my words. And the inflow here is mirrored by the outflow. The outflow is simply a delayed version, a delayed and somewhat twisted, contorted version of the inflow. You could see it here, right? The inflow shot up and remained high, and the outflow shot up, right? Do you see that? Ladies and gentlemen, let us go look at the baseline. Here, it shot up. And with the baseline one, when the inflow shot up, what happens? The outflow also shoots up. It just takes longer to reach that point, but it's like a delayed version with a bigger delay associated with it. It's more sort of delayed till it reaches that same point. Ladies and gentlemen, I would like you now to go and change, and I would invite you to do the low leaving hazard, okay? Okay, now dare I try this? This is going to be a surgical attempt. Okay, here we go. Ready? Here we go. Okay. Okay, sweet success. Okay, so I was able to change it without crashing the software, which I see with considerable relief. Okay, ladies and gentlemen, how about for this case? What will happen? Well, we'll also get a delay just by a much larger amount, okay? It'll be a delayed version of the inflow, but it hasn't yet reached equilibrium. Ladies and gentlemen, I want to ask you this. So at this top graph is showing the inflows and outflows, the bottom graph showing P. Janelle noted that as alpha changes, the equilibrium value of the stock changes radically. Do you see that? What's the equilibrium value when alpha is 0.01? Sorry? 1,000. It's 1,000, ladies and gentlemen. So it's 10 divided by 0.01. In other words, 10 divided by 1 over 100, or 10 times 100, or 1,000, right? That's the equilibrium value of this. If I look at this top graph, however, for every one of these cases, what's the equilibrium value of the outflow? It's the inflow. A first order delay, regardless of alpha, the outflow is trying to approach the inflow. It's trying to get there. Now, in order for that to happen, the stock, for different alphas, the stock will have to be at different levels. If alpha is really small, the stock will have to be at a really high level to make the outflow equal to the inflow. Right? On the other hand, if the stock value is, if the alpha level is really, really high, the stock value can be at low levels and still have the outflow matches the outflow. Okay, now there's a couple key points I want to take away from this. This has been very abstract, but let's think about this in terms of its implications. So one thing, ladies and gentlemen, is that alpha, when we specify alpha, we're specifying the length of the delay. In this case, the outflow is like a mirrored version of the inflow, just with some twisting going on. I would invite you to create, we had a high leaving hazard, maybe create a medium high leaving hazard. And what you'll find, so this would be, medium high leaving hazard, something like that. I would actually copy the high leaving hazard and just rename it medium high. So here we go. So I'm going to call this medium high leaving hazard, okay? And I'm going to have this hazard be 0.2, okay? Let's try running that. Let's try running the baseline first of all, remembering what that looks like in terms of the outflow mirroring the inflow. With the baseline, the outflow mirrors the inflow with a delay, and you can see the effects here. It's delayed. It goes up to the level of the outflow eventually, but it's after a significant delay. In this case, it looks like a delay of roughly, till it gets very close, roughly 80 time units, till it gets very close. Let's try it with the high leaving hazard, right? 0.5. It's approaching the inflow, okay? Approaching the inflow here, but much quicker. By after about 10 time units, it's extremely close to the outflow. With the medium high one, it's somewhere in between. The outflow mirrors the inflow with a certain delay, and the delay is somewhere in between the two top ones, the two others, okay? So here we go. And here it's somewhere in between, so it takes roughly 20 time units to get close to it. In short, all of these, ladies and gentlemen, with different alphas, they're associated with different levels of delay. Yes, it's a rounded version of the inflow, but it's a version. Let's change the inflow a little bit more, ladies and gentlemen. Here we go. Let's go to main, and let's go to the inflow. And ladies and gentlemen, I would like to do the following, okay? I would like to ask, and we're going to put in a little formula here for it. I would like to ask if integer value of time, okay, so if we cast time to an integer, make time an integer, and then I'm thinking how to do this best. We divide it by 5. Okay, divide by 5. Okay, and we say modulo 2. This is going to lead to a waveform, ladies and gentlemen. It's going to lead to a waveform. If this equals 0, then it's going to be if this equals 0, it's going to be 10, otherwise 0. So I'm going to take the time, treat it as an integer, divide it by 5, and then we're going to see if that division is even or odd. If it's even, we're going to have the inflow be 10, otherwise 0. What's that going to lead to? It's going to lead to oscillations. Would you like me to leave that up a little bit longer? People? Do you need this up a little bit longer? Do you want me to put it on a big screen? Do you want me to put up, here, I can put it up in Kate or something like that with bigger font. Or have you got that? This is the modulo operator. It takes it modulo 2, so it's going to go back and forth, be 0, 1, 0, 1, depending on what value this has, this divided by 5. Okay, so let's run it. Let's run it. We're going to see a waveform, ladies and gentlemen, etched out. What's the period of that waveform going to be? Let's go see. What value will it need to take to get back to its original value? You can see it here. So here we have the inflow going up, down, up, down, up, down. And what is the outflow doing? It's following it. It's a delayed version of the inflow with this kind of curvilinear feature. Okay, let's go back and let's make it a less frequent flow. Let's make it divided by 20. Okay? Instead of divided by 2 or by 5, we're going to divide it by 20. What are we going to see now? Well, ladies and gentlemen, right now it's 10, and now suddenly it's going down to 0 now. It's going up, and we can run it here. So, ladies and gentlemen, it's trying to follow the inflow. When the inflow goes up, it tries to follow it. When the inflow drops, it tries to follow it just with a certain delay. If we do the high leaving hazard here, ladies and gentlemen, here we go. If we do a high leaving hazard, it'll quickly equilibrate, and you could see. Now, if anyone in here, who's from engineering background? Who's taken some engineering courses? No one? Okay. In EE, you'd see this sort of thing on an oscilloscope. This is the behavior you see with a capacitor. It drains when you take the current off. It charges up when you have the current. And you see exactly this pattern. Look what the stock's doing. Not surprisingly, it mirrors the outflow. But the outflow is trying to get to the level of the inflow. Then the inflow drops. It tries to get down to the level, tries to get up. It's following the inflow. We call this, ladies and gentlemen, a first-order delay for good reason. The outflow is a first-order delay of the inflow. And we can specify it in terms of an alpha, a chance per unit time leaving this stock. Per unit time, you have, in this case, about a 5% chance per unit time of leaving. Or, alternatively, we could specify it like this. And I'd invite you to save this model. We'll save it as call it model 3 for me. And we're going to change this alpha to instead be mean time in stock. And its value is just going to be 1 over the value of alpha. So in this case, 1 over alpha is 20.0, okay? mean time in stock. Ladies and gentlemen, when you have this situation, and I have slides that will show it for those who are mathematically interested. When you have this situation, you have a stock, and you have a first order delay outflow. The mean time in the stock is simply 1 over alpha. So mean, meaning the average time in the stock that someone who's in the stock spends there. If this is a stock of persons, the amount of time they spend there will be 1 over alpha. Alternatively, we can specify it as mean time in stock, in which case the formula here needs to be what? Instead of being times mean time in stock, it will be P divided by mean time in stock. Okay? Mean time in stock, thank you. And build it and make sure it's a happy camper. Okay? So, ladies and gentlemen, you can phrase these delays in 2 different ways. They are mathematically equivalent. You can specify it as, I'm going to call this mean time in stock 1 over alpha. We can either specify the outflow in terms of an alpha as alpha times P, or we can specify it in terms of a tau, mean time in the stock of what? P over tau. Note the units associated with each of these. Alpha is units 1 over day. It's per day chance of leaving. Tau, ladies and gentlemen, is units of what? If alpha is 1 over day, 1 over alpha is what? Days. Days, ladies and gentlemen. So yes, this is units person per day. This is the amount of mean time in there. So we can specify, it's equivalent mathematically, ladies and gentlemen, to specify our first order delay in terms of a chance per day of leaving, or to specify in terms of a mean time, amount of time in that stock. If you're specifying in terms of per day chance of leaving, per day chance of leaving being alpha, the outflow is alpha times P. If you're specifying in terms of mean time in the stock, the outflow is P divided by tau. And, ladies and gentlemen, the mean time in the stock is always 1 over the chance per unit time of leaving the stock. Alpha and tau are related to each other as reciprocals. So alpha equals 1 over tau, and tau is 1 over alpha. And because of that, these are equivalent mathematically. They're equivalent mathematically. Alpha times P is, well, alpha is 1 over tau. It's the same as P times 1 over tau, or P over tau. Alternatively, P over tau, well, tau is 1 over alpha, so it's P over 1 over alpha, which is alpha times P. They're the same mathematically. Do you see that? Okay, ladies and gentlemen, so we can specify them in terms of either of these ways of expressing them. And we see that, in fact, it is a delay. The inflow here, ladies and gentlemen, is a simple delay of the outflow. We see it most strikingly with this high leaving hazard, right? When we had a high leaving hazard. Okay, we got to be very careful. I did a thing that's very bad. In fact, I sit before you remiss. Oh my gosh. Oh my gosh. Ladies and gentlemen, the mean time in the stock for a high leaving hazard should be what? Apply the learning you have just... Okay, remember the mean time is 1 over alpha. This was the value of alpha for it. So what's 1 over that? Indeed. Okay, low leaving hazard, 0.01. What's the equivalent mean time in stock? If we had an alpha of 0.01, what would be the equivalent mean time in the stock? What does that imply about the mean time in the stock? If we have an alpha of 0.01, what does that imply our mean time in the stock will be? I told you what it is, and I could show you slides that will prove it, where I prove it, but I don't want to lead you through I don't have time to lead you through the beauties of the calculus involved. So what is if we have an alpha of 0.01, what does that imply about the mean time in the stock? It's 100. It's 1 divided by 0.01 or 100. And the medium one, if we had an alpha of 0.2, what would that imply about the mean time in the stock? No, it does not imply a null event loop. 5.0. Yeah. Okay. 5.0. Good. So we now have converted them, except we didn't do baseline yet. Baseline mean, oh wait, we did. Okay. High leaving hazard to, okay, happy. Okay. Great. So ladies and gentlemen, let's run the high leaving hazard here. And what will we see? Well, we'll see it go up and then follow it down. As I said, a first order delay, the outflow wants to be the same as the inflow. If the outflow is less than the inflow, what will happen? Why does the outflow, why do I say this is probably the, other than stocks themselves and flows themselves, this is the most important building block for system dynamics models. So I want you to understand inside out. I say for a forced order delay, an outflow wants to be the same as the inflow. Why is that? What happens if the outflow is less than the inflow?
It's gonna continue to infinity. It's gonna grow.
Okay, if the outflow is less than the inflow, if the inflow is greater than the outflow, what's going to happen?
It's not stable.
Okay, yeah, and the stock will go up, and that will make the outflow go up, and so it chases the inflow, right? It chases after it. It will go up and it will keep on going up until outflow equals inflow. If the outflow is greater than the inflow, what will happen? If the outflow is greater than the inflow, the stock will go down. What will follow if the stock goes down? The outflow will follow, and that will lead to what going on? The outflow getting closer to the inflow. Do you grok that? Grok or not? Okay, cool. Okay, ladies and gentlemen, as I say, I'm hammering this because it's one of the most critical building blocks. It is probably the most critical building block. And if you understand it, you'll get a glimpse of feedback. Here, there's a feedback. You know, the system achieves, it seeks a certain balance. There's also an issue of sort of understanding this as a building block. The outflow is a delayed version of the inflow. Yes, it's kind of twisted in a certain way, but essentially it's a delayed version, delayed by a certain amount. Okay, and the final thing here, ladies and gentlemen, I'm going to ask, what if we do this? What if we do this? What if we save this model, and I'm going to upload these as I am wont to the website, to the Moodle site. I'm going to call this one second order delay. Second order delay. Okay? And what I want to do here is I want to do the following. And we're not going to spend more than 2 or 3 minutes on this at max. So we're going to drag in a new stock, and we're going to call it P2, and we're going to rename the previous one, ladies and gentlemen, to P1. Next, we are going to drag in a flow out from P2, which is going to say overall outflow. Next, we are going to hitch up mean time to stock. To each of those. And in fact, we're going to rename mean time to stock to be mean time in system. It's going to be the mean time in the entire system, ladies and gentlemen. Okay? And to elucidate my thinking more, I'm tempted to do it one way, but time is ticking away, and I want to get you folks out. Yes?
If we change the names
Does it automatically correct? No.
Yeah.
We're going to fix it, but it gives you a choice to do that. You see this little thing here? If you press Control Enter after it, when you change it, it'll actually go and fix all of them.
No, I'm talking about the graphs. And all
The graphs will be modifying ourselves.
Okay.
Okay? Yeah. We're going to need to do it anyway. Okay, ladies and gentlemen. Outflow, I'm going to call, well, we'll leave its name to be that. Now, outflow will be mean time in stock. The outflow will be P divided by mean time in stock divided by 2.0. So it's actually going to be not divided by mean time in stock, but divided by sort of half the time in that stock. Yes, Alexandra.
it's going to be P1.
Sorry, P1. Thank you. Yes, indeed. And then for the overall outflow, ladies and gentlemen, we're going to use that same formula but change it to P2 instead of P1. Okay? So the overall outflow here is P2 divided by the mean time in stock. What I've basically done here, ladies and gentlemen, and we need to have a link here like this from P2 to overall outflow because it depends on it. So what have I done? I have an overall time in the system, and half the time will be associated with the time to go from here to here, and half the time from there to there. And therefore, the outflow here will be divided by some amount of time in this stock, which is half the overall time, and same thing here. Again, I do it more beautifully if we had time, and I'm going to build the model. And it is a deeply unhappy camper. Okay, so let me go see. It says mean time in system is not used, but is depended on. Oh, okay, yeah. Instead of saying mean time in stock, it should be mean time in system. Sorry. Mean time in system. And the same thing for this guy here. Mean time in system divided by 2. Okay, we're getting closer. The final thing we have to correct, so again, this is mean P, so this is the average time they'll spend in this stock, and similarly for this guy, it's the average time they will spend in this stock as mean time in system divided by 2. The final thing we'll need to do is to go up here, and we will have it, go up here, and we will plot out here, instead of outflow, we'll plot out overall outflow. Okay? Overall outflow. And we have to change it here, overall outflow. There we go. Great. And similarly, for down below, we have to change it to be based on Now I'd like to do so this will be total people, and this will be P1 plus P2. Okay? Sum of them. The total number of people in the entire system. Okay, this is what's called a second order delay. Do you recognize what it's made up of? It's made up of 2 first order delays. Each of them has a mean time associated with them of half the mean time in the system. They're simply staggered. I want to let you folks go, so I would invite you to run this and observe the results. And I want to pose for next time the question, how do these results differ from the results we saw just a few minutes ago with a single first order delay? This is a second order delay. It is a successive staging of first order delays. So this one is a first order delay depending on P1 with half the amount of mean time in system. This one depends on P2 in the same sort of way.
Initial value P2?
P2 is 0 initially. Thank you. 0. Okay. And ladies and gentlemen, if you run it, you will see somewhat different behavior that we saw last time, and I want you to tell me how that is. Okay? So that's all for today. We'll talk about some of the implications of this for next time. And we will then continue on to a discussion of a little bit of competing risks, and we'll get closer to talking about nonlinear models as well. Okay, this is a linear model. We'll soon be seeing nonlinear. So check this out, and you be prepared to discuss your investigation next time. I will be posting these as well. Okay, I'm going to hold office hours in 341 for people who are interested in the breakout room over there, rather than 386 because that room is now occupied. Great.
Thank you, sir.
Thank you very much. Okay, I will see if I can go over this for next time.
Okay. Perfect.
Okay? Yeah.
Next week, not. Or for.
If I can do it by Thursday, it's going to be a stretch to do it by Thursday, but if I
so
can,
that's next week.
I will. Okay? Okay, very good.